All right. So our next speaker is Raghav, Malik, and the talk is Coyote, a compiler for vectorizing encrypted arithmetic circuits. This is from Purdue University.
All right, am I audible? Yeah, okay, cool. Hi, I'm Raghav. I'm from Purdue, and this is my talk on Coyote, a compiler for vectorizing encrypted arithmetic circuits. This is work that I did with, in collaboration with Kabir, Sheth, and my advisor, Milind Kulkarni. I want to start with a little bit of background on fully homomorphic encryption, which basically refers to any encryption scheme that lets us compute directly over ciphertexts without having to decrypt them first. So specifically what that means is, let's say I've got two parties, we'll call them Alice and Bob. Let's say Alice has two numbers, X and Y, she can encrypt them and send the ciphertexts over to Bob, who can add the ciphertexts together and get back an encryption of X plus Y, which Alice can then decrypt. Now it's called fully homomorphic because it lets you add and multiply ciphertexts. And with these two operations, we can essentially simulate any kind of like bounded depth computation. For a bit more background on FHE, most FHE implementations treat ciphertexts as giant polynomials, or this is sort of how they're encoded. And this has a couple of consequences. First of all, it means that homomorphic operations over ciphertexts are incredibly slow. And in particular, multiplication is a lot slower than addition. But there's an upshot to this encoding, which is that polynomials give us built-in vectorization. In other words, I can take a whole vector of plain text values and encrypt them into a single ciphertext polynomial. And then computing with this like vector ciphertext polynomial corresponds to sort of like adding and multiplying at each element of the vector. And so it sort of lets us think about our FHE computations as happening in this vectorized context. And then finally, one sort of unique facet of computing with FHE is that control flow can't depend on any secret data. So specifically, that means any for loops have to be fully unrollable, so their bounds have to be known at compile time. You have to inline all function calls, and if you have branches, then you either have to know which branch you're taking at compile time, so like the condition has to be like plain text, or you have to do something where you execute both sides and you select the correct output at the end. And in particular, this last point means that it suffices to think of all of our FHE computations as essentially just being giant arithmetic circuits. We don't have to worry about any kind of control flow or anything like that. Okay, so that's background. Let's talk about what the paper is actually about. The high-level idea here is that FHE is really cool, but it's really slow, and we can try to recover some of that performance by vectorizing. And so our specific contributions are, first of all, we have an FHE-aware algorithm for vectorizing these arithmetic circuits. And we implement this algorithm in a vectorizing compiler and a DSL called Coyote. Now, I called our vectorization algorithm FHE aware, but let's talk about why that's actually necessary by first looking at what vectorization looks like outside of the FHE context. So the sort of standard example of vectorizing is when you have a data dense loop like this. So I'm iterating from 0 to 16, and I'm like incrementing one array with values from another array. The standard thing I can do here is unroll my loop by, let's say, 4 times. And now I get 4 copies of essentially the same instruction. I can pack these into a single vector instruction, and I'm done. This is great, but if you remember from before, in FHE, we can't really rely on the presence of control flow structures like loops, and we'd like to be able to vectorize more general programs than just ones that look like this. Fortunately, there's a vectorization technique that can help us here called SLP, or superword level parallelism. This example is essentially lifted directly from the SLP paper. There's a reference to that at the bottom there. But SLP lets you take arbitrary sequences of code like this, and it sort of identifies which instructions don't have any data dependencies between them and also have like isomorphic operations, and it lets you vectorize them this way. Okay, this all seems very cool, but to understand exactly why SLP doesn't just magically solve our vectorization problem, let's take a look at what vectorization actually means in an FHE context. Okay, so we have a number of vector operations available to us. We've got a plain text, ciphertext, add, and multiply. This is very cheap when one of the two operands is a plain text. We've got ciphertext, ciphertext, add. This is also relatively cheap because we're just adding polynomials. We've got a ciphertext, ciphertext, multiply. This is very expensive because multiplying polynomials is expensive. And finally, the only operation we have that lets us move data from one vector lane to another is the cyclic permutation, which I'll call a rotation. And basically what this does is it takes everything, it takes all of these sort of elements in the vector and shifts them over by a fixed number of slots. So in particular, this is really the only way we have to like align our data up before doing vector operations over it. And so the thing to notice here is there's no like gather scatter instructions or pack unpack instructions. And specifically what this ends up meaning is that because that rotation operation is so expensive, we have to be very careful about not incurring too much like data movement overhead when we're generating our vector schedules. So let's take a look at a specific example where this kind of comes up. I have here an arithmetic circuit, and a priori, this looks like it should be a very good case for vectorizing. We've got 4 adds at the first level, so we can kind of pack those together into a single instruction. We've got 2 multiplies at the second level, so we can pack those together. And then up at the top, we've got a single add, so we may as well do that in scalar. Now, the thing to notice about this schedule is R1 and R3 here are sort of produced in the wrong lane compared to where they're used, and so is R5. So in order to make this actually work, I have to insert 2 rotations in between. Now, taking a look at what's happened here is by vectorizing, we've saved 3 adds and 1 multiply, but we've incurred a cost of adding 2 extra rotations. And if you remember, the multiplies and the rotates are the really expensive instructions, and the adds are relatively cheap. And so it turns out that this schedule is actually not worth it. And in fact, by attempting to vectorize our code, all we've done is make the performance worse. All right, that's bad, but can we do any better? The answer is yes, and I've got a schedule here on the right that sort of does this the right way. And the way to think about how we can actually get to the schedule is if we look at these two edges that we rotated along last time, we can think about just contracting them away and sort of like deleting the edges and then taking their endpoints and identifying them in the circuit. And just for a bit of terminology for the rest of the talk, I'll refer to this thing as a quotient circuit, or like a quotient of the original circuit. Now, applying our same vectorization technique from before on this new circuit, we find that we actually get exactly the schedule that we want, right? So first level, we've got 2 adds. Second level, we've got this sort of super node where we align the adds and then the multiplies. And then at the third level, we've got that last add. Now, the only thing that's produced in the wrong lane here is R5, so I can insert a single rotation to make that all work out. And now I've saved 2 adds and 1 multiply at the cost of 1 rotate. And this schedule is much better. Now, there's 2 important things to notice here. First of all, I've sort of like implicitly chosen the correct way of assigning nodes in the circuit to like vector lanes. And if I chose incorrectly, then this actually would not be a good schedule at all, because I would have a bunch of things that could be aligned properly, but I just didn't align them. And so I would have a bunch of extra rotates. So there's this sort of like hidden step of like figuring out where everything should go. And the other thing is the trick we played here, and the reason this actually works, is that by contracting those edges, what we've done is force certain operations to happen in scalar, and we've stopped ourselves from over-vectorizing. And it turns out that this is exactly the way that Coyote thinks about doing all vectorization. So you might notice we have a whole spectrum of vectorization policies available to us. On one end of the spectrum, we have the very aggressive like SLP style approach, and this corresponds to not collapsing any edges, or you can think of this as like quotienting by trivial circuits at every node. On the other end of the spectrum, we could worry only about the data movement and not about vectorization at all, and just end up doing everything in scalar. And you can realize this as sort of like collapsing every edge or like quotienting the circuit out by its connected components. Of course, both of these ends of the spectrum are probably not what we want, and so finding a good schedule essentially amounts to like choosing some kind of quotient in between, or like picking some subset of edges that we actually want to collapse. The way Coyote does this is we frame it as a sort of graph search problem. So we have this graph of quotients. Every vertex in this graph, one of these big circles, corresponds to like a quotient of the original circuit. So you can see you've got like the root node, and then every edge corresponds to contracting one of the edges of the circuit. And all we do is just search this graph to find the best possible quotient and use that to generate our schedule. Now, I've said the phrase best possible quotient, but what does our cost model look like? How good is a quotient? Well, the answer is it's as good as the best lane mapping it admits. So if you remember from before, every scalar instruction in the code has to be mapped to a specific vector lane, and different choices of these mappings can result in different like numbers of rotations that we might need. And so they can like result in more or less efficient schedules. So specifically, every step we take through the graph, we have a new circuit. We have to re-optimize the lane mapping at that step. And this lends itself to like a 2-layer search strategy, where the inner layer we do like simulated annealing and find a good lane mapping for that particular circuit quotient. And then on the outer layer, we just do a beam search over the graph and use the costs from that lane mapping to guide this search. Okay, that's how the vectorization works. Let's talk about the DSL. So Coyote is a DSL that's embedded in Python. This gives us a couple things for free. First of all, Python automatically unrolls the loops and inlines the functions just as part of like executing the program. And in fact, this lets us stage away all plain text computation and just produce a circuit. So specifically, if you have like a conditional with a branch that's like known at compile time, or like a branch that only depends on plain texts, Python will just execute that conditional and give you back the circuit in the right direction. The DSL also lets the programmer specify whether they want certain inputs to be replicated or unreplicated. This is kind of an important point, so I'm going to talk about it a little bit more. You can see I've got two sort of abstract depictions of circuits on the right here. We've got this circle input that's sort of being passed in two different ways to the square at the top. And we've got two choices. So we could either pass the input in once and then rotate it once to get it to the right place, or we could pass in two separate copies of the inputs and just have them go in the right places automatically. So this is sort of like a design decision that's left up to the programmer, but it does have some impacts on performance that we'll see later. The other thing is the programmer can specify that some set of their inputs should be packed into vectors. So let's say you're writing a matrix multiply, maybe you want all n² elements of the matrix to be like passed in as a single input vector. So the DSL just has like things for that. And then Coyote takes this stage circuit and it vectorizes it and it compiles it all the way down to C++ and links it against like an FHE library that supports the kind of vectorization we care about. Okay, so for our evaluation, we ran a handful of benchmarks. I've sort of displayed a subset of them here. Each benchmark we ran in 3 different ways, one with both inputs unreplicated, one with only one of the inputs replicated, and one with both inputs replicated. For the sort benchmark, which is like sorting a list of numbers, we also had this like ungrouped thing, which basically means all the inputs are replicated, but none of them are packed into vectors. There's the speedups show like the speedup over scalar, so how much faster it is compared to if we didn't vectorize at all. A couple things that I want to point out here. First of all, you'll notice that we always do better than scalar, and we actually in some cases see pretty significant improvements of like 3 or 3.5 times faster than if we didn't vectorize. And the other thing is it's almost always better to replicate all of your inputs, the exception being the dot product benchmark, where like everything's only used once, so it really doesn't matter if you replicate or not. And this is kind of a key point where FHE vectorization is sort of different from your like traditional vectorization. Because normally you may not want to replicate all of your inputs because replicating it means that you use up an extra vector lane, and the only thing you're saving is like not having to do this extra movement, but like your data movement might be relatively cheap anyways because you've got like a select instruction or whatever. But in the FHE world, we've got access to like thousands of vector lanes. Like our vectors are very wide, so that's not much of a price to pay, but it's the data movement that we really care about. And so our sort of cost model looks different and our trade-offs look different, and so we end up making different decisions for that. Okay, so in conclusion, Coyote is a compiler that lets you vectorize arithmetic circuits, and it keeps a FHE-specific cost model in mind when it does that. We find that it can minimize the data movement overhead by vectorizing at the level of subcircuits. This is by like contracting those edges instead of working at the level of instructions. And we see that Coyote can find optimal data layouts that encourage more efficient rotation patterns. And finally, we see that on a number of benchmarks, the vectorized code is significantly faster than the scalar code. If you found this interesting, please check out the paper. There's a QR code for that. The paper contains a lot of other cool stuff, like more benchmarks. We have some case studies, and we have some sample code if you want to see what Coyote actually looks like. All right, that's it. Are there any questions?